Threading in Python isn't about parallel execution. It's about concurrent I/O multiplexing within a single interpreter instance. When you call threading.thread, you're not creating a new process. You're registering a new execution context with the OS scheduler, all constrained by the global interpreter lock. Let me show you the bytecode and real benchmarks. When Python executes thread target equals func.start, here's what actually happens. First, pthread_ create syscall on POSIX systems allocates a new OS thread. The CPython interpreter then initializes a pythread state struct containing the execution frame stack. The GIL is a mutex lock, implemented as pthread_mutex_t on POSIX. Every 5 milliseconds by default, the GIL check counter forces a thread switch. That's 200 context switches per second, each costing 1 to 3 microseconds of overhead. The GIL operates at the bytecode instruction level. When thread A holds the GIL and executes bytecode operations like binary_ADD, the interpreter checks every 100 opcodes. During I/O operations, the GIL is explicitly released via pyeval_save thread, allowing thread B to acquire it. This is why requests.get shows perfect thread scaling. The C extension releases the GIL during socket I/O system calls. That's the key. I/O releases the GIL, computation doesn't. Real benchmark downloading 100 files from localhost. Sequential, 47.2 seconds wall time. CPU time, 2.1 seconds. That's 95% I/O wait. With 5 threads, 10.8 seconds wall time. Speedup, 4.37 times. Why not 5 times? Context switching overhead, 0.3 seconds total. Memory analysis. Each thread allocates 8 MB stack. For 5 threads, 40 MB overhead. Now CPU bound, computing SHA-256 hashes. Sequential, 3.8 seconds. With 5 threads, 4.1 seconds. Actually slower. The bytecode shows why. Call_function acquires and releases the GIL 5,000 times. Context switching between threads waiting for the GIL adds 0.3 seconds overhead. The solution? Multiprocessing bypasses the GIL entirely. Pro optimization. ThreadPoolExecutor uses a work queue. The internal worker function blocks on queue.get, which calls _queue size protected by a lock. For optimal performance, set max_workers to minimum of 32, or CPU count plus 4 for I/O. Use threading.local for thread local storage. It creates a separate namespace per thread, avoiding lock contention. 6.9 times faster than locked counters in my tests. If you want to see more, like and subscribe.